All right, here we go. Unit 5 is, in my opinion, the most important unit. It's not the most difficult because we've already done the most difficult in my opinion. The most difficult was Unit 4 because it was so much so fast. Unit 5 is where you can make or break yourself, okay, as far as momentum. You can fix things now. No, it is not too late. If you look at the back of the room over there on that big old poster, there's Unit 1, 2, 3, 4, 5 is that first big, huge thing, and there is a lot of information. Then Unit 6 is even bigger. Unit 7 is less, and Unit 8 finishes it off. Unit 9 and 10 over there in purple, that's for BC Calc topics. So all those blue ones, they're just for AB Calc. Okay?
So is the BC stuff not going to be on our AP?
The BC will not be on your AP exam.
But we're still learning it?
No, you're not learning it.
Oh, we're not learning it?
No, that is like a class overview for both AB and BC.
Okay.
So that teachers could just get that and know exactly what we were needing to teach students for that year. Yes?
So BC, all you learn is those two.
Those two more, but those two is a lot of information in just those two more. Okay?
So they do those two the whole year?
No, they don't do that the whole year. So our AB class just covers all of AB. At schools, including ours, next year when it says BC, what it really means is ABC, which is all those 10 units in 1 year.
But if you've done AB and you do BC.
Yeah, if you've done AB as a junior, next year you can take BC, and it's going to be a lot of review. You're just going to twiddle your thumbs and get nice grades for a while, and there at the very end, like about February, then you'll actually start learning new stuff. January or February. So, here we go. With this unit, I'm not even going to lie, this unit is so important that I will, like I did with my Algebra 2 classes. So my Algebra 2 classes are right now learning how to factor quadratics and how to do a lot of like factoring skills, which are huge. All the algebra that they are doing right now, in my opinion, are the foundations of a student before they come into calculus. So to incentivize them, I've promised, since I teach 4 classes, whoever gets the highest test average, I will buy you a pizza party before we go to our Christmas break. So I'm going to do the same with you. The highest average between you or second period will get a pizza party.
We already won.
Whoa, easy.
Let's go.
I'm recording, Brady. All right, so I'm going to have to edit that video. Anyway, so the higher average will get a pizza party, because this is really, really important stuff. Now, it's easy information, but it is a lot of information that you have to memorize to a very detailed level. Easy information, but a lot. You got to memorize every little detail too. I mean, you'll see here just very soon. Okay. So what I kind of give the analogy is, you got quadratic formula factoring, or you have completing the square factoring. Quadratic formula was much, much easier, but it took forever to do. And completing the square factoring, if you know what you're doing, is a lot faster and more efficient. So what we're doing is a quadratic formula analogy. A lot of information, way easier than last unit, but there's so much more to pay attention to. The math is easier, but the attention to detail is big time involved. Okay, here we go. So, in pre-cal, you learned extrema this way. So, maximums and minimums. A minimum will occur basically when everything else is bigger than that one piece that you're looking at, which makes sense. And the same thing with the maximum, when you, or the thing that you're evaluating, is the biggest thing compared to everything else. That goes without saying. You can look at a graph, and with pre-cal, you were looking at f of x for that. Calculus, it's different. We're not going to look at old f of x. We're going to use f prime of x. Much more efficient, much more accurate, okay? And you can do this all by hand. And what is it that we're trying to do? We're trying to find the mins and the maxes of graphs. Ultimately, in this unit, it's trying to find the mins and maxes of just things in life. Like, when can I achieve the max profit? When can I achieve the minimal costs? When can I achieve, you see what I'm saying? The maximum strength of a design, let's say, of a wing of an airplane before it cracks. Things like that. Okay? Here we go. Definition of relative extrema. So a relative extrema is looking at local maxes and local mins, not the absolute. Okay, so I will let you look at this and read it a little bit carefully, more in depth, but I don't want to read all these words because a lot of it you're not really going to register. You have to see it and start working with it to understand what's going on. So let's move on to this figure right here. I have a figure from -2 all the way to 4. And I'm talking about the domain here at this endpoint all the way to 4, including 4 and including 2. Subtle details, but important. So f has an absolute maximum at what? An absolute maximum at x equals 4. What is the maximum? 21. So we'll say the maximum is y equals 21. Absolute minimum at x equals -2. You need the x for sure. And the minimum value is what? -15. These are absolute. So we could say absolute is the same as global. Like you are the max, you are the min or whatever, globally. There's no one else more max than you or more min than you. However, we also have relative max and mins. And a relative is not everyone included, it's just a small little sample. Okay? So this is more local. To where if I were to say the local maximum at what would you say from the graph? X equals 0. So we could say, like x is equal to 0, the max, that is the relative max or local max, is y is equal to 5. So we could say like Frisco is right here, Frisco High School, and their math program is a local max. Maybe around the surrounding areas like Plano or Lovejoy, Frisco is the local max. But the absolute max is where we are, right? Okay. So now you know the difference between the local and the absolute. And the truth. Okay. So f has a relative minimum at what? X equals 2. And that minimum is y equals 1. Alright, so let's keep going. So, relative versus absolute. The next thing to understand for today, because there's a lot, is what is a critical point? Critical point is, what is the important point? When I look at a graph immediately, I want to be able to see, is this worth looking at? What's worth looking at? Because if I had a graph that looked like this, guys, can you tell me how many critical points, how many important points do you see on this graph right now?
4.
There's actually 6.
Oh, 6.
1, 2, 3, 4. It's probably what you were all thinking. But endpoints are also very important. Okay? Yeah.
What if it's like there isn't an end point and it just goes to infinity and negative?
So we'll look at that in just a bit. Nice. So what if we have this same graph, but we're looking at cusps? Now how many critical points do I have? Still 6. 1, 2, 3, 4, 5, 6.
Because you can't derive at endpoints either.
Non-differentiables are cusps, endpoints, vertical tangents. You with me? Jump discontinuities, things that I cannot derive. But the ones that I can, that will equal 0, are the ones that are the max or mins of a slow curve function. Do you understand? Do you understand? Because that right there, those slopes are 0. But if it's a cusp, it's non-differentiable. You can't derive at a cusp.
Oh, so it's non-differentiable or at 0, right? Or like.
Yep. So the definition, I wanted you to see it first, of a critical number is when f prime of c is 0 or f prime of c is undefined. How do I achieve for something to be undefined? Because in the calculator I could do this. I could do the solve feature when f prime of x is equal to 0 comma x, and it would spit them all out. How can I set something equal to undefined? When is something undefined?
When it's divided by 0.
When it's divided by 0. So you could set this to, 1 over 0. That's basically saying, guys, if we get a derivative function, this is how you'll do it by hand, and you're going to do it mostly by hand. Let's say that we get a derivative function that has a top numerator piece and a bottom denominator piece. If I want to find when they're equal to 0, set the top equal to 0 and solve for the x's. If I want to see when they're equal to undefined, set the bottom equal to 0, and you will find the critical points for the undefined. So a lot of these functions, guys, that you get fractions, you're just going to set the top equal to 0, bottom equal to 0. All those zeros are going to be your critical points. Real quick, critical points are just the important ones. If I'm looking at a graph, is that important? No, it's not important. It doesn't tell me that it's about to become a min. It's in between important points, but that is not an important point. Important points, we're going to only deem important points as those that are equal to 0 or undefined. Omar.
Wait, you said top equals to 0 is, when do you do that?
The top is equal to 0, grade for grade, whenever you're looking at relative max and mins.
So you do the 1 over to find
The 1 over to find the bottom with the calculator. Some people ask, how do you set it equal to undefined? You can either set the bottom's denominator equal to 0. You know what I mean? Like we could, let's deem this as like, whatever this is, we're going to call it f prime or just f. You know what I mean? And this would be like g of x. So if I set g of x, whatever we get down here, equal to 0, I can solve for it. Or I could set the whole f prime equal to 1 over 0, which is undefined, which is a cool trick that the calculator already figures out for you. All right, critical numbers. That's concept 2. That's very important to know. Relative extrema, relative, local, only occur at critical numbers. So here we go. In the following examples, name the maximum and minimum points if possible. Arjun, what's the minimum? What do I write? Minimum at what, Arjun? 0. At x equals 0, right? What is the minimum? Y equals 1. Attention to detail. All these little things we have to know how to write it and stuff. Because more is coming, a lot more. The maximum. Rovik, what's the maximum going to be?
x equals 2, y equals 5.
Yep, x equals 2. So at x equals 2, y is equal to 5. So guys, what is the max? If I asked you what is the max, what do you say?
Y equals 5.
Y equals 5. Where does the max occur? What do you say? at x equals 2. At or where versus what. So at or where is your input x value. What is it? Is that output y value. All right, Braden, let's do the next one. The minimum is at what?
X equals 1.
And what is it?
It is 1. Y equals 1.
Y equals 1. Oh, here we go. Jordy. What is the maximum at? So since it's open, we know it's not at 2. It's right before 2. So how do you show the maximum?
Get the limit at that point.
Okay, so look, let's call this f of x. If I say the limit of f of x as x is approaching what? 2 from the left. This is where it would occur. But we don't say x is equal to this. So can you denote it? You can't.
Could you just say like 1.9 repeated?
Nope, because you could get even closer than 1.9 repeating.
But that's
Theoretically, you could get closer. So here's what you say. Here's what you say. Because it's not defined and it's not colored in, you're going to have none. There's not going to be a max.
because it can only be at the
It can only be at the relative maximums or the absolute at endpoints. This is not an endpoint. It's like you're getting infinitely close to this endpoint, but you will never max out. Theoretically, you cannot max out as you continue to approach something. Yeah.
On the test we had, wasn't there a question? It was like one that derivative.
So it was different than this. That one was asking what was the steepest that. So it's different context. But it is a correlation. Yeah. But for this one, I want you to put none. Okay. All right. So minimum. This last one. What's the minimum, guys?
x equals -1.
There is no minimum. For the same reason, you will infinitely approach x is equal to 0, but you will never reach it. So there's really no minimum.
So what is the point at x equals -1? It's just nothing.
At x equals -1?
Yeah.
So this is a point, but it's not a relative max or a relative min because it's not, you know what I mean? It doesn't have both one-sidedness to it. It doesn't have like wings, if you will, like a bird. It doesn't have left and right. It just has one wing. And it's non-differentiable if it just has one wing per se. Okay? What's the maximum?
X equals
No, what's the maximum?
2. Y equals
Y equals
I can't see.
5, right? Where's the maximum? X equals 2. All these subtle things you'll see when we start asking questions. You have to know it. So here we go. What conditions are necessary to guarantee that there will be a maximum and a minimum?
Differentiability.
Must be continuous. Not differentiability, only continuous. Yeah, so look. It will guarantee that there will be a max or a min and a min only if it's continuous. Because you could have a cusp that's continuous, but it's not differentiable anywhere, but that's still going to be a min. Because critical points say that the critical points occur when the derivative is 0 or undefined. Cusps are undefined. Okay? All right. Questions, because all of these, they're huge conceptual understanding. Okay? Again, so many questions come from this section on the AP exam. Multiple choice with or without calculator, free response with or without calculator. The extreme value theorem. There's so much. There's so much to learn in this unit. If f, look at this, is continuous on a to b, then the function attains an absolute max or, and it should say and or, an absolute min for some value of C between A and B. Did I just draw a continuous function?
Yes.
I could say this is A. I could say that this is B. And what this is saying is, first of all, looking at this, do you see a max? Where's the max at? At x equals B, right? Where's the min at? X equals A. So extreme value says if it's continuous, then it will have a max and it will have a min. You with me? That's all that is. Now, I know it goes without saying, but what if I had this? What if I had from A to B a straight horizontal line? Think about this. Let's say that was y equals 2. What's the max? 2. Y equals 2. What's the min? Y equals 2. Okay? Where are the critical points? Everywhere. Everywhere between A and B. Because 0 is the slope. And the endpoints are what? Non-differentiable, which are undefined.
Wait, why are the endpoints non-differentiable?
Because you can't derive an endpoint. You can't take the derivative of an endpoint. So if I look at a graph, I can take the derivative here because I have graph to the right and graph to the left of it.
Oh, that's what you're saying, right?
Yeah. But if I have an endpoint, I have graph to the right, but I don't have graph to the left of it. In local linearity, when we did way back when with limits, we need both-sidedness. As you approach C from the left and from the right. Remember that? You need continuity before you get differentiability. Are we good?
So that means A and B are not.
They are critical points because they're endpoints. Endpoints will always be critical because they're undefined. Their slopes are undefined. They're non-differentiable. Okay, and you'll clear it up on this next thing right now, and you'll understand what I'm talking about more. Our first major theorem per se, proof or whatever you want to call it, is candidate's test. Okay. This is about to feel a lot like, remember when we did continuity, guys? And the proofs that we would show with continuity and all the work that we would do? And then we did intermediate value theorem as well, and it has to satisfy these conditions, K has to be in between f of A and f of B, so on and so forth, and then it would guarantee that there was one C value in between A and B, all that stuff. If you're like, what? Yeah, oof, that was a lot. Well, we're about to do some more of that, okay? Candidate's test. Here we go. Candidate's test is looking for only absolute, otherwise global, max and mins. It's not looking for local. It's looking for the Ohio State, the max or the minimum. Okay? Not a minimum or a max, that's Fresco. It's looking for the max. Prosper. The minimum. I don't know. Alright, so find f prime of x and the critical numbers in the domain A to B. Alec, how do I find critical numbers? What did you learn today that we find critical numbers by doing?
Find the derivative.
And we set it equal to what?
0 or does not exist.
Yep. 0 or does not exist. Undefined, right? So functions are undefined, limits do not exist, and derivatives, they can be undefined as well. Okay? Because a derivative being undefined just means that whatever you get for your derivative function, you could have a 0 on the bottom. That's what f prime equals undefined means. Alright, next one. Evaluate, that should be evaluate, not evaluate. So evaluate f at each one that you find in step 1. So all the ones that you find, we're going to see what is that y value. 3, not only will we find the ones that we found with step 1, but we're also going to include our endpoints. And why do we include them, Braden? Why are we having to include the endpoints? Because they're non-differentiable. They are critical and important just the same.
How come it's parentheses then if you are?
Because these parentheses are saying at those endpoints. Not just before, it's saying at those endpoints.
Oh, you're on 3.
Oh yeah, we're on 3. 2 means between those endpoints. So let's do all of these in blue, and we'll do my endpoints like in gray for boundaries. Alright, here we go. So, what's so important? Wait, go ahead.
So I don't know if this has anything to do with anything, but when we did like continuity in IVT, you would specify that when we did the, I don't know if this
Keep going.
on like the points, like the intervals, you would have to specify that it was on or at, not in.
Mhm.
What's the difference between that?
On is like on an interval. At is only 1 point. So on an interval means, like if I had this A to B, when I say on A to B, I'm talking about from A to B, not including A and not including B.
But is there a difference between saying on and in?
No.
Oh.
No, I prefer on though. Don't say in.
Okay.
Okay, and then at means at a specific point. Let's say I said at A. Then I'm talking about only right there. Okay. Here we go. This is where all the details come into play, guys. So much is about to happen, okay? And the candidates test is the first, it's the easiest proof, if you will, or justification it is to do. Your goal is to justify. So guys, when you go to court, and you're there in front of the jury, and you have the attorneys, the prosecuting, the defense attorney, you have to show as much evidence to prove your innocence or whatever. You have to show the evidence. And what this justification is, it's all about the evidence. You have to show all this evidence to the smallest detail. So here we go. The first thing that we're going to mention is f of x is continuous. Okay? And I might have jumped the gun on that just a little bit. I'm actually trying to do mean value theorem right now. This is coming the next slide, but not right now. So you don't need this until the next slide. My apologies.
So this is just candidates test that we're doing?
Yeah, we're just doing the candidates test. Here we go. So to find the absolute max and mins, when you see this magic word right here, absolute, you're going to go immediately to candidates test. That's your first go-to. There's other forms, but you'll learn them next class. So we're going to start off this question by saying per candidates test. So you're looking for the pers and the becauses. This is your proof of justification. So per candidates test, we're going to look for our critical points. So here we go. F prime of x is equal to what? Anyone?
6x minus 24.
Will this have an undefined? No. But we were going to get it from here, right? We're going to get our candidates or our critical points from here. So the only way that you can do it is just set it equal to 0 and solve for x.
Is it not squared?
Oh,
I
did
mean,
I?
it's not, is what I'm.
Oh, my bad. I don't know why I put squared. Oh, and I highlighted it. All right, so let's take that away. Let's take that away. Nice catch. Thank you, Nate. GCF. We're going to do a lot of these by hand. So let's get in good habit. GCF out that greatest common factor. So what is my only one that you see? 4. So guys, we're going to make a table with candidates tests. And the best way to remember that is this is a T. This is a T, and this is a T. So that's a T. And I'm just joking. But candidates test is going to have a table. That's your work. That's your justification. I'm going to label all my candidates. All right, line up, guys. Line up all you important candidates because I'm going to evaluate your value. Or evaluate your value. Okay? So what's the first one that's important? 4. Right here. What we just did were the number 2 critical ones. The ones that were in between A and B that were either 0 or undefined. What are the other ones important? Automatically. Endpoints. -1 and 5. Because they're non-differentiable. The slope is undefined. Guess where we're going to put these values in? The original equation. Guys, we've been doing this a lot lately, especially. We will find an at value, and in implicit differentiation, we plug it into the original function, and we plug it into f prime, because it has important stuff on both levels. So when I put in -1, by hand, we got to get fast, we're going to use synthetic substitution. So the coefficients of my x squared x and constant term in descending order. If I'm going to plug in a -1, I'm going to copy, multiply, add. Multiply, and then add.
That's 20, 26.
Oh, what did I do?
28.
I don't know why I put that. So what will my value be? 26. So this right here is the y, oh my gosh, I keep doing that, is the y value right there. If I were to do it again, but this time I'm going to evaluate it at 4. We have 3, -24, -1. This time we're going to plug in our candidate of 4. Copy, multiply, add. Multiply, add. So that my y value is -49. Real important. Okay, the last one. Let's just plug it in. 5 squared is 25 times 3 is 75. So 75 minus 5 times 24 is what?
Wait, say that again?
5. So what I'm doing right now is a different method, just plugging them in to see what I would get. You see how it's a little bit more difficult because some of these numbers are big. So I just wanted to show you just real quick, because sometimes you can make a simple error. You could do that with synthetic substitution, as I did too, but it's all good. It's reduced errors. So we have 3, -24, -1. We're going to try this 5. Smaller numbers. 15. What's -24 plus 15? -9. So you get -45. So I get -46. If you are understanding this, what word do I put right here above f of x to describe what I'm looking at? What goes here? Where goes here? So what is the value at -1? It's 26. So it's 26 where? At x equals -1. Do you understand? Okay. So this is how you're going to answer. You've done all this work, and the most important work I'm leaving, I'm not erasing. Not only will we, after all this work and saying per candidates test, we're going to put the absolute max equals what? Equals 26 at x is equal to -1. The absolute min equals what? -49 at x is equal to 4. Questions so far? Your answers are lengthy, guys. There's a lot. There's a lot to answer for sure. Yeah.
So as part of the work and answer, do we have to make the table?
Yes. All this that I've written down is required for sure. Like from the problem down.
So this test won't be like a calculated test, that's why we're showing this synthetic situation.
Yeah, most of it, yes, nice observation. Most of it is non-calculator. Very, very, very little of it is optimization, or with calculator, that will be optimization. And you'll see that whenever we get to it. And you have a quiz before you go on Thanksgiving break, and our test, I think, is the second week or something like that. It's the week before finals week is when your test is for this unit. It's like that Thursday and or Friday, whatever it is. And then the next week is finals week. Am I recording? Yes, perfect. There's a 91 to 100 question review that I will share with you for the AP exam. And it's basically practice and do everything. Most of the semester final, most of the questions correlate with what you're doing here in this unit. So that's a good thing, most of it. And when I mean most of it, I want to say like 60% of your final comes from this unit. The rest of the year is fair game for the final. But needless to say, the review that I will put online for you, you can start now. And it would be a nice idea when you do have time to start now. You don't want to try to cram that test. 15 or 20 minutes here or there from every other day until your final is my best advice to you. Okay? Each and every single one of those questions has been individually recorded. And there are quick links that I will help you use, that I will help you find to get to them just like that. Yeah?
So our final's gonna be like a mock AP exam, but like only for the first half of
Yep.
the English.
So yes, the mock AP exam, of all the things that you've learned, it will be cut in half. And it's exactly it's half of what a real exam would be. And yes, I'm still recording. It is going to be graded on an AP scale. So those 70 points that I told you, if you get like a 67% or something like that, which is like 71 points out of 108, something like that, you will automatically get a 90 because that's a 5 on the AP score. You understand what I'm saying? And I think it's like if you get a 70% mastery is what it is, 70 or 71% mastery, that's 100 in the grade book. And I've had people out of the 108 last year, someone got, or 2 years ago, someone got 106. And it was only because they missed like 2 negatives or something, or 1 negative.
So the final exam is going to be like multiple choice,
The final exam will be half multiple choice, half free response.
which is like the AP exam.
So what we're going to do is we're going to give you the free response first, so that we can grade it throughout the week, so that when we give you the multiple choice the second day that we see you, or whatever it is, the way it pans out, you're just going to do the multiple choice part. And then immediately we can just use ZipGrade to see exactly what your score is, so we can put it in the grade book as fast as possible. Okay? Questions? Yeah.
So like the 100-question review, is it like AP style questions as well?
Mhm. And I was just feeling extra, whatever, ambitious when I recorded those videos years ago, and I even put a timer so that you could see how long it should take you to do each of those problems. Yeah.
And the test, is it going to be like the time limit, the approximate
Yeah, the final exam is pretty much whatever window of time they gave us, we took every minute. So if it's a 2-hour window that we get, you're going to be testing those full 2 hours. If it's an hour and a half, you're going to be testing those full hour and a half. Because it's paced off of that.
But like the tests we've been having now, are they like
The
time
unit
limit?
test,
Like the unit tests, are
the
they,
same,
they're based off.
based off the speed that we've been doing.
Okay, yeah.
Yeah, so the test that you have next unit is on a 100-point scale. Just treat it like you've been doing all these tests.
Yeah.
The final exam, just know that you have a little bit of cushion in your brain of, yeah, I don't have to get a 90% to get a 90 in the grade book. Okay?
Or like no, I meant like is the unit tests we've been having now, like the amount of time we've been having is approximately
The same.
Okay, yeah.
All right, here we go. So our next example for absolute, because we still have this, and then we're going to look at Rolle's theorem and mean value theorem. Here we go. So for practice, I'm going to run through this a little bit, pick up the pace. I'm going to use, for candidates test, we're going to find the critical points. F prime of 0, or sorry, F prime of x. This right here, rewritten, is that. So help me out. What's the derivative?
2 cosine x.
Or 2 sine of x, right? The cream. Don't change the cream. And then multiply by the derivative of the cream, which is what? Cosine of x. And then it's plus a negative sine of x. Because of that piece right there. So there's the derivative. Are we going to be able to set this equal to undefined? No, because there's no fractions with x's in the denominator. So we will just set this equal to 0. For the sake of time, I'm just going to put 0 right here. And now we're going to solve for x. What do? Let's factor this. Pull out a sine of x. GCF. Perfect. Pull out a sine of x, and all of this is left over. 2 cosine of x minus 1. So we have two pieces that we're going to set equal to 0. This one and that one. Which if I do a little bit of math, a little bit of magic, it's the same as that. So you tell me, when is the sine of x equal to 0? 0. Do I put 0? Okay. Is that it?
No.
Let me ask you. What did I tell you the domain was, or the range that is, for arc sine and arc tangent? Pi over 2 to pi over 2. Remember that?
Yeah.
And then arc cosine was here to here. Which one are we doing? Arc sine. So what answer should I put? And pi and 2 pi. Because of attention to detail. When is the y value 0? At 0 degrees, at pi degrees, or pi radians that is.
Yeah, but we're just saying arc sine, right?
But look what they gave us.
So you use that theorem when it's only asking for one answer. If it's asking for on the entire thing, you use however many answers
Yep.
there actually are.
We are being told where our answers will exist, Braden. They're telling us evaluating between 0 and 2 pi, list all the answers that would be 0.
Yeah, so then why did you show us that arc sine?
Just to make sure you don't confuse the two and only say 0.
Oh, yes.
Okay? But you have to still know this for the final exam. That's what I'm trying to still keep in your mind. I'm trying to prevent data dumping as much as possible and connect things at the same time for memorization purposes. Yes, Amy?
But like if you were to make a table, wouldn't you have included those points too?
Yeah.
So like how many would
It was just a coincidence. On this one, it was a coincidence. All right, so let's find out when the cosine of x is 1/2. When is the cosine of x a positive 1 half.
Pi over 4.
No.
No.
Pi over 3. Because this is 1 half root 3 over 2. Or else? Oh, nice speed. 5 pi over 3. Because 5 pi over 3, it also is 1 half, but a negative root 3 over 2. So all the candidates that I've found, I'm going to go ahead and make the table now, okay? So the candidates that I found, and Amy's absolutely correct. It was just a coincidence on this, but the first ones that I would list out are these right here. 0 to 2 pi. You know for sure that those are going to be candidates because they're endpoints, non-differentiable, no wings. What goes here? F of x, because that's where we're going to be plugging in these candidates. Okay? And then now just list out all the f primes that you saw that were 0 or undefined. Okay, so I'll just add pi over 3, and 5 pi over 3. Everything else is accounted for. They don't have to be in order. Nope. Because you're going to evaluate them anyway. So now we got to be good. We got to be fast. Oops, not there. This is why we practiced with our 4-minute drills in pre-cal. Remember, this is sine of x, quantity squared. So what's the sine of 0? 0. Square? 0. What's the cosine of 0? 1. So 0 plus 1? 1. Let's now plug in where those great places are. We're going to plug in our next candidate up to back. Our next candidate is pi. What's sine of pi? 0 squared? 0. What's cosine of pi? Negative 1. This one's a little bit different. What's the sine at pi over 3? Root 3 over 2. Nice. Square it? 3 over 4. What's the cosine at pi over 3? 1 half. Or 2 fourths. So you get pi fourths. 5 pi over 3. Picture it. So negative root 3 over 2. Square it. Still 3 over 4. What's the cosine at 5 pi over 3? 1 half. So it's still 5 fourths. 2 pi. What's the sine at 2 pi? 0. Square it. 0. What's the cosine at 2 pi? So it's 1. So what is the absolute max? 5 fourths. At x equals what? Pi over 3 and 5 pi over 3. What is the absolute min? Negative 1 at pi. So absolute min equals negative 1 at x is equal to pi. Everything that you see is required. The pers, the because, well, there's no because yet. It's coming though. Cool? Yeah. Where? Oh no, it's understood. Like by default, you're in radians. Look at your attention to detail though. I like that. Cool. Alright, so now, new concept. We're going to look quickly at mean value theorem. Mean value theorem is saying a function is continuous on a to b. So if I have, here we go, a to b, and I drew a continuous function, whatever it is, and I have endpoints, because it says have endpoints, I just drew the graph. Okay? It's got to be differentiable between a and b. Do y'all see a graph that's differentiable everywhere between A and B? Yeah, because there are no what? Cusps. There's no jump discontinuities. There's no vertical tangents. There's no removable discontinuities. Okay? Then there is at least one C value, at least one, that is in between A and B. That means somewhere here, there's going to be a C somewhere. It could be closer to the B, it could be closer to the A, wherever it is, it's in between A and B. Where this f prime at C, that means the slope at C, will be the same as the slope between the endpoints. This is the tangent slope. This is the what? Come on, guys. The secant slope. You've been doing the secant since algebra 1. y2 minus y1 over x2 minus x1. So this is the color coordinated slope. And in calculus, now what we're doing is we are identifying, we're finding all the C's that have the same slope. How many do you see right now? How many C's will there be between A and B? There will be 2. One's about here. Look at that parallel. Same slope. The other one is about here. So this is C2 and this is C1. You could see this in other notations. Let's say I multiply both sides by B minus A. So B minus A times f prime of C is equal to fb minus f of A. You've done linearization recently, right? So linearization wanted a value from an initial value. So if I move my f of A all the way over here, and I added it with my b minus A, and I multiplied with f prime of C, it would equal f of B. It all means the same thing. You've been doing it since algebra 1. Y equals mx plus b. Okay? Questions? So sometimes people like to steal credit. And this mathematician was like, you know what? I noticed something. And it all revolved around, okay, you ready? This mathematician took mean value theorem and wanted it to be in the history books. So with mean value theorem, what this mathematician did is they were like, oof, what if the f of A and f of B were the same? See, I didn't show them the same. I showed one way down here and the other one way up here. But what this mathematician said is like, Rolle's theorem was like, what if these are the same? What if f of A started here, then did some crazy business, and f of B start or finished at the same height? You with me? It almost feels like intermediate value theorem. But you're not putting something in between two y values. You're saying that the y values are equal. All right, let's figure it out. First of all, I've drawn a continuous function with an endpoints at A and B. Have I also drawn it to be differentiable everywhere?
Yes.
Yeah. No vertical tangents, no removable discontinuities, no cusps. Then there's at least one C value, and I see why you're saying N. See, these notes I've borrowed, they're not necessarily my created notes, but the lady who gave them to me is phenomenal. teaching calculus for 35 years. On is going to be in between A and B. Do you see at least one that will say the tangent is equal to the secant? What's the secant slope, guys? 0. And the secant slope is 0 because this piece right here is the same. It could be 20 minus 20. Look. Let's say that's 3. 3 minus 3 is what? 0. So it doesn't, B minus A, whatever this is, 0 over that number is still going to be 0. And that's when f prime of C is equal to 0. Does that make sense? So what you're really looking for is, when is that happening? You with me? So there's no really 3 there. How many do y'all see? 1, 2, 3, 4. He wanted credit. He took what was there and he made it his own. And all he identified were the relative max and mins. That's it. Good for him, right? And now, there's my first one. Here's my second one. Here's my third one. Or, yeah, right there. There's my fourth one.
So they're basically the exact same thing.
They're the exact same thing, only this is a type of mean value theorem.
How? But on both of them, there have to be at least one where the slope is equal to 0.
Yeah.
Oh,
No, not necessarily.
Not
No,
zero,
do you
like
hear what he
equal
said?
to.
Not necessarily. It doesn't have to equal 0. Because look, what if I had a continuous function from A to B? Look at the secant. Could there exist a C here to where its slope would also be the same as the secant? Yeah.
Well, that's just what that is.
That's all it is. Right? I know this almost feels like the example that I gave you of 1, 2, 3. What's the max? 3. What's the min? 3. What? You know what I mean? It kind of feels the same. Are we good?
Yeah.
Look for the homework website. I might even include the Delta Math where you haven't decided yet which one's better. But that's all you have for today.